So to better understand the computation for the pre-stress loss due to the still stress relaxation or due to still relaxation, we can apply it in a sample problem. So this is the sample problem. A pre-tension pre-stress beam has a span of 15.2 meters or 50 feet as shown. So where is the pre-tension pre-stress beam? So this is the pre-tension pre-stress beam, which has a tendon profile like this, harp tendon profile, which is usually the case for pre-tension beam or pre-tensioning. And this is the actual pre-stress beam or pre-tension beam, which is actually a simply supported beam that carries a uniformly distributed load. So these are given in the questions. So the question asks to find the relaxation loss in pre-stress at the end of 5 years, assuming that the loss from elastic shortening and from long-term loss due to creep and shrinkage over this period is 20% of the pre-stress at transfer. Assume that prior to transfer, the jacking force on the tendon was 0.75 FEU. So again, the pre-stress beam is pre-stress, or I mean pre-tension, and then obviously it will undergo several losses in pre-stress due to several reasons like elastic shortening and creep and shrinkage. So after 5 years, the questions the question asks what what will be the estimated magnitude of the relaxation loss in the pre-stress after 5 years after this pre-tension beam here uh, already experienced the losses that are supposedly be that are supposedly will be experienced by it, assuming that the sum of the elastic shortening and I mean, assuming that the loss of pre-stress due to the elastic shortening and the creep and shrinkage of the concrete over the period of 5 years is approximately 20% of the pre-stress at transfer, and assuming also that that particular pre-stress at transfer is approximately equal to 75% of the ultimate strength of the pre-stressing reinforcement. So other given on the problem are this. So at midspan, the cross-section of the beam is like this with dimensions specified on the problem, and the distance of the pre-stressing reinforcement to the bottom equal to this. And then other parameters are given: FC prime, FCI prime, FPU, APS, which is a 1/2 inch diameter 7-wire strand, which has an area equal to 99 mm squared or 0.153 inches squared, and we have 10 of those. And then the magnitude of the pre-stressing steel, the magnitude of the modulus of elasticity of the pre-stressing reinforcement is approximately equal to this 186,200 megapascal, or approximately equal to 200 megapascal, 200,000 megapascal, which is actually the modulus of elasticity uh, of steel. And then FPY is equal to 1586 megapascal, which is stress relief. And that's all for the given information. So for us to solve for the uh, pre-stress loss due to relaxation, we first need to find the magnitude of the force at transfer, which is usually equal to this magnitude of the jacking force minus the pre-stress losses due to still stress relaxation. Although it was mentioned in the problem that before the actual transfer, the force on the tendon or the pre-stressing reinforcement is approximately equal to 0.75 FPU. So we can use that magnitude instead of computing for this or finding for this items here or parameters here. So that can be approximately equal to the 75% of the ultimate strength of the pre-stressing reinforcement. which is equal to 1862 megapascal. So therefore, we will just substitute the magnitude of FPU. We can find that the the pre-stress at transfer is actually equal to 1396.5 megapascal. And then after transfer, after 5 years after jacking, according to the question, uh, the losses that will be caused by the elastic shortening, creep, and shrinkage over that particular period is just 20% of the pre-stress at transfer, which is this. So therefore, the remaining pre-stress after the losses that were mentioned on the problem or already occurred will just be equal to the 80% of this, the pre-stress at transfer, which will be equal to 1117.2 megapascal. And if we will try to compute for the ratio of the FPI prime and FPY, which is this and the given FPY, we can see that it is greater than 0.55, uh, which is the criteria that was mentioned a while ago for using the formula for pre-stress loss due to relaxation of steel. And then since we know that we need to find the number of hours after jacking to find the pre-stress loss due to still relaxation, because we know that still relaxation is actually a time dependent pre-stress loss. So we need to find the particular time that uh, that we are concerned here in finding the pre-stress loss due to still relaxation. So the given time is 5 hours, 5 years, and we know that in a year there are 365 days, and we know in a day there are 24 hours. Therefore, the total hours for that period of 5 years is just equal to 43,800 hours. So since we already found out all of the parameters needed for this, so we use this because it was mentioned in the problem that the pre-stressing reinforcement is stress relief, and we know that this is the formula for stress relief wires and strengths. So all we have to do is substitute all of the corresponding values here. So the FPI prime is this, the T time is this in hours, ratio of FPI prime and FPY is equal to this. So we just have to substitute it. We just have to substitute them, and computing computing this equation, we can see that the pre-stress loss due to steel relaxation after 5 years is just equal to 80.07 megapascal. So you can expect that after 5 years, after the pre-stressing reinforcement already lost 20% of its magnitude due to the elastic shortening and creep and shrinkage, it will also develop a pre-stress loss due to the relaxation of the pre-stressing reinforcement with a magnitude equal to 80.07 megapascal. So those that is one way to compute what we have discussed a while ago is one way to compute the magnitude of pre-stress loss due to steel stress relaxation. So actually, we have another method for accounting for relaxation loss, which is made by ACI-ASCE committee. So this is actually a joint committee. So they specified a certain method for computing pre-stress loss due to steel stress relaxation, and it can be found on ACI 423.10, which is the guide to estimating pre-stress loss reported by Joint ACI-ASCE Committee 423. So the particular provision for the uh, computation of pre-stress loss due to steel relaxation uses the separate contributions of elastic shortening, creep, and shrinkage in the evaluation of the stress relaxation loss. So, unlike the formula given a while ago, which is just dependent on the time after jocking and the FPY of the pre-stressing reinforcement, as well as the stress being experienced by the pre-stressing reinforcement at time t after jocking in hours. So instead of that, for the method of ACI-ASCE, uh, it uses the separate contributions of elastic shortening, creep, and shrinkage in the evaluation of the still stress relaxation loss. So the particular provision for computation of still stress relaxation uh, can be found on section 5.4 of the ACI 423.10, which is this, the relaxation of tendons. So the formula is actually this. So that is how you can find the pre-stress loss due to still stress relaxation according to ACI-ASCE method. So the values of KRE and J here can be found on this table, which is dependent on the tendon type that is used on pre-stressing. And if you will refer on PCI 2010, you can see similar table such as this, which this can be found on this reference actually, and can also be found on the PCI the PCI Design Handbook 2010. They are almost the same. They are almost the same. So you can see here that the pre-stress loss due to still stress relaxation is a function of the shrinkage loss, creep loss, and elastic shortening loss of elastic shortening loss of pre-stress. So for the value of C, if you can notice, there is a C here. So for the value of C, the value of C can be found on section 5.4.1, which specifies a certain way of how to compute the magnitude of C depending on the ratio of FPI and FPU. So this is for stress relief strand, and this is for low relaxation strand. So for the other values of C, the pre-computed, actually this you can use this way, this method to compute the value of C, but you can also use these values of C that can be found on PCI 2010. So actually, if I'm not mistaken, they will just resolve to the same magnitude. The PCI 2010 just uh, pre-computed all of the values of C depending on the ratio of FPI and FPU. Say for example, if the ratio of FPI over FPU is equal to 0.8 for stress relief bar or low relaxation strand or Y, the corresponding value of C will be equal to this 1.28. So you can use both of them, both methods. The method specified on the ACI 423.10 or the values of C that can be found on PCI 2010, the predefined values of C. So for simplicity, you can use this because the values of C are already predefined, unlike on the method specified on the ACI 423.10. You still have to compute for the value of C. So this is easier to use. Also, although you can use both of them, any of them, uh, it depends on your preference and the preference of the problem. If it wants to, if it wants you to use the ACI 423.10 or the specified or the predefined values of C that can be found on PCI 2010.